you find a piece of a skull. It's buried deep in the earth in a cave in some remote valley. It's clearly old. It doesn't look like a modern human skull. The brow ridge is heavy. The jaw is robust. You think it might be important. Maybe it's a Neanderthal. Maybe it's an early Homo sapiens. The first, most important question is a simple one. How old is it? Let's say the lab eventually tells you it's 100,000 years old. How in the world did they know that? Nobody was there to mark a calendar. There's no born on date stamped on the bone. The answer is that they don't date the fossil itself. Not usually. They date the world around it. So, it's a bit like finding a newspaper next to a coffee cup. You know the cup was left there on the day the newspaper was printed. Scientists do the same thing, but with rocks, dirt, and atoms. They are geological detectives. And for a fossil that's 100,000 years old, they have a whole toolbox of techniques because that age is a bit tricky. The first tool most people think of is carbon dating. We've all heard of it. Carbon-14 dating. It sounds perfect, but for our 100,000-year-old skull, it's completely useless. It doesn't work. The reason is simple. Carbon-14 just doesn't last that long. Here's how it works in a nutshell. There's a special kind of carbon in the atmosphere called carbon-14. It's radioactive, which means it's unstable. It slowly falls apart, or decays over time. Cosmic rays from space are constantly hitting the upper atmosphere, creating a steady supply of new carbon-14. This C14 mixes with regular carbon in carbon dioxide. Plants breathe this in. The animals eat the plants. You eat plants and animals, so while you're alive, you are constantly taking in a little bit of carbon-14. You have the same proportion of C14 in your body as the atmosphere does, but the moment you die, you stop eating. You stop breathing. You stop taking in new carbon-14. The C14 already in your bones and tissues starts to decay, and it isn't being replaced. It decays at a very predictable rate. This rate is measured in a half-life. The half-life of carbon-14 is about 5,730 years. That means if you start with a pound of C14, in 5,730 years, you'll only have half a pound left. After another 5,730 years, you'll have a quarter of a pound, and so on. Scientists can measure the amount of C14 left in organic material, like a bone or a piece of charcoal. They compare it to the amount of stable carbon, carbon-12, which doesn't decay. The ratio tells them how long it's been since the organism died. It's a brilliant atomic clock. But here's the problem. After about 10 half-lives, there's so little carbon-14 left that it becomes almost impossible to measure accurately. It's just gone. 10 half-lives for C14 is roughly 57,300 years. So for a fossil from, say, 40,000 years ago, carbon dating is fantastic. For our 100,000-year-old skull, the carbon clock has long since wound down. There's nothing left to measure. It's like trying to tell the time on a watch whose battery died a month ago. So if carbon dating is out, what do? This is where the real detective work begins. Scientists have to switch to other clocks that tick much, much slower. And these clocks are usually found not in the bone itself, but in the geological layers surrounding it. The most fundamental idea here is stratigraphy. It's a simple concept. Layers of dirt, sand, and rock build up over time. The stuff at the bottom is older than the stuff at the top. It's called the law of superposition. When paleontologists are excavating a site, they are incredibly careful. They use tiny brushes and dental picks. They map everything in 3 dimensions. They are not just digging up a bone. They are reading a story written in layers of earth. The exact location of that skull, in its specific layer, is the most important piece of information. Because if you can date that layer, you can date the skull. So, how do you date a layer of dirt or rock? You look for things in that layer that can be dated. One of the most powerful tools is based on a different radioactive element, potassium. This leads to methods called potassium-argon dating and its more precise cousin, argon-argon dating. These methods are perfect for places with volcanic activity. Think of the Great Rift Valley in Africa, where so many of our ancient human ancestors have been found. It's a volcanically active region. When a volcano erupts, it spews out ash and lava. This material contains a radioactive version of potassium called potassium-40. Potassium-40, just like carbon-14, decays over time, but it decays much, much more slowly. Its half-life is 1.25 billion years. It's a clock designed for geological time. When potassium-40 decays, one of the things it can turn into is argon-40, which is a gas. Now imagine molten rock or lava deep inside the earth. It's hot, it's a liquid. Any argon gas that forms can easily bubble out and escape into the atmosphere. The molten rock is essentially argon-free, but when that lava erupts and cools down, it solidifies into rock. The minerals in the rock form crystals, and these crystals trap any new argon gas that is produced by the decay of potassium. The clock starts the moment the rock cools. So, let's go back to our dig site. Maybe our skull isn't in a volcanic area, but maybe 110,000 years ago, a volcano hundreds of miles away had a massive eruption. It would send a cloud of fine ash across the landscape. That ash would have settled down, creating a thin, distinct layer. Later, our human ancestor dies, and their body is buried in mud and sand on top of that ash layer. Then maybe 90,000 years ago, another volcano erupts, and another layer of ash settles on top of the layer containing the fossil. The scientists can find those two ash layers, one below the fossil and one above it. They take samples of the crystals from each ash layer, they take them back to the lab and use lasers and mass spectrometers to measure the ratio of potassium-40 to argon-40. They find that the bottom layer of ash is 110,000 years old. They find the top layer is 90,000 years old. This tells them something incredibly valuable. The skull is younger than 110,000 years and older than 90,000 years. They have bracketed the age. Our 100,000-year-old estimate fits perfectly within that bracket. This method has been the workhorse for dating many of the most famous hominin fossils in Africa. It gives us solid, reliable bookends for the age of a find. But what if there are no volcanoes? What if our skull was found in a limestone cave in Europe or Asia? There are no ash layers to help us. Scientists need a different clock. This is where another family of techniques comes in, called uranium series dating. There are different types of uranium series dating, but one that is particularly useful for our 100,000-year-old problem is called uranium-thorium dating. Like the other methods, it's based on radioactive decay. Uranium-238 decays into a whole series of other elements, one of which is thorium-230. The key here is how uranium and thorium behave in water. Uranium, it turns out, dissolves in water. It can be carried around by groundwater seeping through the earth. Thorium, however, does not dissolve in water. It's insoluble. This difference is the secret to the clock. Think about a cave. The water drips from the ceiling full of dissolved minerals. As the water drips, it leaves behind tiny deposits of calcium carbonate. Over thousands and thousands of years, these drips build up to form stalactites hanging from the ceiling and stalagmites growing from the floor. This rock is called flowstone, because the water flowing into the cave contains dissolved uranium. That uranium gets locked into the crystal structure of the flowstone as it forms. But because thorium is not dissolved in the water, the brand new flowstone contains uranium, but virtually no thorium. The clock starts. The trapped uranium begins to decay into thorium. Over time, the amount of thorium in the flowstone builds up. The scientists can take a sample of this flowstone. In the lab, they measure the ratio of uranium-238 to thorium-230. Since they know the decay rate, this ratio tells them exactly when that layer of flowstone was formed. This method is incredibly precise and works well for ages from a few thousand years up to about 500,000 years. It's perfect for our 100,000-year-old skull, so how does this help? Imagine our skull was washed into the cave and buried in sediment. Then, for a long period, water rich in minerals flowed over that sediment, creating a hard layer of flowstone right on top of the fossil layer, sealing it in. If scientists can date that layer of flowstone, they know the fossil must be older than that. If they are lucky, they might find a fossil sandwiched between two layers of flowstone. Just like with volcanic ash, they can bracket the age. Even better, sometimes a crust of this mineral deposit forms directly on a fossil bone. By dating that crust, they can get a minimum age for the bone itself. It's a powerful tool for cave sites. But there are other methods too, which use a completely different physical principle. These are called trapped charge dating methods. The two main types are thermoluminescence TL and optically stimulated luminescence OSL. These methods don't wonder the fossil, and they don't date volcanic rock. They date the dirt the fossil was buried in. Specifically, they can tell you the last time a grain of sand was exposed to sunlight. It sounds like magic, but the physics is straightforward. All around us, in the soil and rocks, there are trace amounts of radioactive elements like uranium, thorium, and potassium. They are constantly emitting radiation. It's a very low level of background radiation, but it's always there. Now think about a grain of quartz or feldspar, common minerals in sand and silt. These minerals have a crystal lattice structure. When radiation from the soil passes through one of these grains, it can knock an electron out of its normal position. Most of these electrons just fall back into place, but some of them get stuck in tiny imperfections in the crystal. They become trapped. This happens constantly, year after year. The longer a grain of sand is buried in the dark, away from sunlight, the more of these trapped electrons it will accumulate. It's like a tiny battery that is slowly charging up. The amount of charge is a measure of how long the grain has been buried. So how do you read this clock? You have to be incredibly careful. The scientists go to the site and take a sample of the sediment from the same layer as the fossil. They do this in complete darkness, often at night with a special red light, and put the sample into a light-proof tube. Any exposure to sunlight would erase the signal, resetting the clock. Back in the lab, under safe light conditions, they pour these grains of sand onto a special instrument. For OSL, they shine a beam of a specific color of light, like blue or green, onto the grains. This light gives the trapped electrons a little jolt of energy, enough for them to escape from their traps. As they escape, they release their own tiny flash of light, a luminescence. The instrument measures the intensity of this light. The brighter the light, the more electrons were trapped, and therefore the longer the grain was buried. Thermoluminescence TL is similar, but instead of using light to release the electrons, it uses heat. They heat the sample up, and as it gets hotter, it starts to glow as the trapped electrons are freed. The reset mechanism is sunlight. When that grain of sand was blowing around in the wind or being washed down a river, sunlight was constantly hitting it. The energy from the sun was enough to knock all the trapped electrons out of their traps. The clock was at 0. The moment that grain of sand was buried alongside our skull, it was in darkness. The clock started ticking. OSL and TL, therefore, don't tell you when the fossil was formed, they tell you when it was buried. For most purposes, that's just as good. This method is incredibly versatile because quartz and feldspar are found in sediments almost everywhere on Earth. There's one more major method that's particularly useful for our time frame. It's called electron spin resonance, or ESR. It works on a similar principle to luminescence. It also measures the buildup of trapped electrons from background radiation. But instead of measuring light, it uses microwaves and magnetic fields. And crucially, it can be used directly on certain materials, including tooth enamel. Tooth enamel is a very dense, crystalline material. It's the hardest substance in the body. When a tooth is buried, its enamel acts just like those grains of quartz. It starts to accumulate trapped electrons from the natural radiation in the surrounding soil. By taking a tiny piece of a tooth from our 100,000-year-old skull, scientists can use ESR to measure the total radiation dose it has received since it was buried. To turn that dose into an age, they also need to know the dose rate, how much radiation the tooth was getting each year. So they also have to measure the radioactivity of the soil, sand, and rock that the fossil was buried in. They might even put a little dosimeter probe into the wall of the excavation trench for a year to get a direct reading. Once they have the total dose from the tooth and the dose rate from the soil, they can do a simple calculation, age-ed, total dose rate. And ESR is a fantastic tool because it can sometimes date the fossil directly, not just its surroundings. Teeth are so durable, they are often the best preserved parts of a fossil. Combining ESR dates from a tooth with OSL dates from the sediment around it can create a very strong case for the age of a find. Now, the most important part of this whole process is that scientists never, ever rely on just one method or one date. They cross-check everything. The real confidence in a date like 100,000 years old comes when multiple different methods, based on different physical principles, all point to the same answer. Let's imagine the ideal scenario for our skull. It was found in a cave. The team carefully excavates it. They take samples of the sediment from right around the skull for optically stimulated luminescence dating. They notice a thin layer of flowstone just above the skull, and they take a sample of that for uranium-thorium dating. Our skull has a perfectly preserved molar tooth, so they take a tiny sample of that for electron spin resonance dating. Back in the lab, the results start to come in. The OSL date on the sand says it was buried 105,000 years ago, with a margin of error of about 8,000 years. The uranium-thorium date on the flowstone says it formed 98,000 years ago, plus or minus 5,000 years. This makes sense the skull must be older than the rock that formed on top of it. The ESR date on the tooth comes back at 102,000 years old, with a margin of error of 10,000 years. Now look at those numbers. OSL says around 105K, ESR says around 102K, UTHET says it has to be older than 98K. Everything is consistent. All the different clocks are telling a similar story. This is when scientists can confidently stand up and say this fossil is approximately 100,000 years old. What if the dates don't agree? That's also incredibly useful information. It tells the scientists that the story of the site is more complicated than they thought. Maybe the skull washed into a much older layer of sediment, so the OSL date for the sediment is much older than the ESR date for the tooth. This is called a disturbed context, or maybe a river carved through the site, jumbling up layers of different ages. When dates conflict, it forces the researchers to re-examine the geology of the site and figure out what really happened. It's all part of the detective work. So dating a 100,000-year-old fossil is not a single event. It's a process. It's an investigation. It starts with careful excavation, understanding the layers of the Earth. It moves to the lab, where different atomic clocks are used clocks based on the decay of potassium in volcanic ash, the decay of uranium in cave formations, or the slow buildup of trapped electrons in grains of sand and tooth enamel. And it ends with cross-checking, with making sure that the story told by one clock matches the story told by all the others. It's a painstaking, difficult process, but it's how we turn a single, silent piece of bone into a data point on the vast timeline of human evolution. It's how we know where we came from and how long it took to get here.